Today we're going to look at copper extraction. And this makes up 3 points in the C2 specification, and we're right at the end of C2 in part 6. Now this is higher tier only, so if you were on the foundation tier, you do not need to look at this video. So in general, what we will be looking at today is the extraction of high quality ores, that's ores that contain a high percentage of copper, the extraction of low quality ores, and how we then purify what we get at the end. So firstly, looking at high quality ores. Now I want to really be clear here, the specification does not ask for much detail on this at all. But we need to be aware that ores come in different qualities because that will determine how we extract them. Now high quality ores for years have been the method of extraction that we have prioritised because it contains the highest percentage of copper, which means that you're getting more per tonne of rock that you extract. But the issue we have nowadays is that those high quality ores are running out. They are another example of a finite resource. Now the methods that we've used to extract copper in this way are as shown on the screen. So one method is smelting, and smelting here is more commonly identified when we talk about the extraction of iron, and it's about using carbon to produce and to reduce, I should say, the ores to produce copper. We can also use sulfuric acid and react that with oxide compounds of copper, and then we can purify this using other separation techniques. Now that's all well and fine, but in order to get to the point where you either can do smelting or extraction with sulfuric acid, you have to mine these ores out of the ground. And industrial mining is a huge undertaking. Not only is it incredibly expensive, but it has a huge environmental impact. We will eventually run out of this ore if we continue to mine it at the rate that we currently are. And also, the environmental impact in terms of pollution, visual pollution, and the displacement of natural habitat is a real serious consideration. So nowadays, what we have are some more sustainable methods of extraction of copper. And we say that these are methods to extract low quality ores. And when we talk about low quality ores, we're talking about ores that contain a lower percentage of copper. These traditionally would have been ores that had not been bothered to be extracted because it wasn't financially viable using traditional methods. However, we've now got 2 bio methods. These are biological methods, so named because they involve living things. Now they're quite simple, but the language around them can be a bit confusing. So let's talk through them. So the first one we have here is phytomining. Now, phytomining, the way I like to try and remember that is that P for plant, phytomining. Now, phytomining is where you sow the seeds of plants over an area where there is a low quality ore. Now, talking of low quality, this image is not very high quality at all. But in the ground underneath this plant will be an area of low quality copper ore, an area where you find a lower percentage, but a percentage nonetheless, of copper ions within the soil. Over time, what happens when you plant these plants is that these plants absorb copper ions via active transport into the plant themselves. This happens over a very long period of time because obviously you're having to wait for the plant to grow. And when I say very long, I'm not talking years and years, but I'm talking longer than if you had to mine it. Now, when the plants are at a reasonable size and they have absorbed enough copper, what happens is these plants are harvested and then they are burnt. Now, when they're burnt, they leave behind ash, and that ash has copper compounds, and that ash can then be used and purified to produce purer copper that can be then used for other chemistry, etc. What I'd like to do now is to pause this video, and I would like you to write a brief outline of how phytomining is used to extract copper ores. What you now have is a short set of steps there that I've written down for you so you can check your answers. So plants are grown on low-grade ore, plants absorb the ions, the copper ions, plants are harvested and then burnt, and the ash contains copper compounds. Now, advantages and disadvantages, because this is a really key topic that the exam board like to ask you compare and contrast questions. So first of all, this is a slow process. We're waiting for plants to grow, and as they grow, they absorb these copper compounds. So it doesn't happen overnight, and therefore it is a more long-term strategy for extracting copper. However, the advantages of phytomining is that you do not need to do as much industrial mining. And this is a really good thing for loads of different reasons. But one of those reasons is it actually conserves the high-grade ores. So it means that we don't use quite as many of those high-grade ores, so they're around for longer if they are then needed down the line. And that links into sustainability. It also reduces waste. When we mine for copper ore in a traditional way, yes, we do extract the veins of copper ore, but we also are left with lots of excess rock. We don't want to process all of that rock. It doesn't all contain copper ore. And so you have lots and lots of waste. And that does really get piled up around mines. So that's one process. The second process we can look at is called bioleaching. And bioleaching is actually really simple for what you need to know at this stage. Now, the image I can show you here is, I think, a really nice one. So if you were looking at making revision notes, this would be a really good way of dual coding your revision. So this here shows phyto extraction or phytomining, where you grow your plant over the copper ores. And here is bioleaching. And bioleaching is using specific bacteria that absorb copper ions from the soil around it to produce a acidic solution that contains copper ions. And that is pretty much it. The bacteria absorb copper compounds from the soil that they are placed, and that means that they then can produce this solution that we call a leachate, and that contains copper compounds. So pause this video, see if you can give me a summary of bioleaching for your notes. So, welcome back. And here is just some quick steps. Like I say, guys, for what you need to know, very, very basic at this stage. So bacteria break down low-grade ores into an acidic solution containing copper ions. This is called a leachate. That's the name of that solution. Now, again, this is really useful because it's a way of obtaining that low percentage of copper that you find in these low-grade ores in a much more gentle way on the environment. But I say gentle, it does have some issues, bioleaching. One of those issues is that it does release toxic byproducts, such as sulfuric acid. And sulfuric acid, we know, is a strong acid. It has a very low pH, which means it can be very damaging to the environment around it. And so it's obviously something that would need to be monitored very closely if there was an area which was undergoing bioleaching. Now, phytomining and bioleaching are really, really important methods that we have taken on in order to obtain resources from our earth in a more sustainable way. Okay, they're really important processes. But at the end of those two processes, we don't end up with pure copper yet. And so we need to also be aware of the purification techniques to obtain that. Now, these two things are things that you have done before. They are not new, but it shows you how chemistry links together. So one way that we can purify copper, and when we talk about purification, we're talking about taking copper from its ions, which might be copper oxide, it might be copper sulfate, it might be copper in another form. And how do we react it or do something that's going to end up with pure copper on its own? So the first thing we can do is we can extract copper with iron. Now, if I make this a little bit larger so you can see it, this is the reactivity series of metals. If you look at where copper is, it's down here toward the bottom. It's quite unreactive. Up here, we find iron. Now, if I react a copper compound with iron, and this again can be iron which is left over from other industrial processes, so we can be quite sustainable here, then what happens is the iron displaces copper in the compound that it was previously in, which will lead us with copper being left over. This is a displacement reaction, and it's a very, very common reaction that we have studied already. So it's utilising this iron, because iron's more abundant than some of the others around here, and doing a displacement reaction so we get copper on its own. The other alternative is we can do electrolysis. Again, a very simple diagram here of electrolysis, and it's something that you have looked at before. Electrolysis, by definition, is using electricity to split compounds. So if I had, and this particular scenario here is a electrolysis of a copper oxide compound, I can see that at my cathode, which is my negative electrode, I am getting positive copper ions attracted there, and I am forming a layer of copper on the outside, And on the other side, on the anode, I am attracting the negative oxygen ions and producing oxygen gas. These are both perfectly adequate ways to purify copper to end up with pure copper that then can be used for other methods and other techniques. So that's all you need to know for this section on copper. In our next section, we will look at either the life cycle assessments if you're on the combined syllabus. If you're on triple, there will also be a video on alloys, rusting, and the properties of different metals and how they're used.